In this video, I will explain the difference between absolute and conditional convergence, and I will present a theorem related to absolute convergence. As motivation, consider the following example. Is the sum of sine of n over n squared a convergent series? This series is not positive. Sine takes both positive and negative values, so I cannot use comparison test. But it is also not an alternating series. The pattern of positive and negative values of sine is more complicated than purely alternating. Then I'm out of ideas. What can I do? Would it help to first look at the same series but with absolute values? Maybe there is a relation between them. This second new series is positive, so at least I can use comparison test on it. But will it help me answer the original question? More generally, I want to find out what is the relation between an arbitrary series and the same series with absolute values. It would be great if we could reduce the problem of convergence of arbitrary series to only positive series. There is a theorem that helps us with this, although only half of the time. This is called the absolute convergence test. Given an arbitrary series, if the same series with absolute values is convergent, then the original series is convergent as well. I am going to represent this in a little table. An arbitrary series may be convergent or divergent. The same series with absolute values, since it's a positive series, can only be convergent or infinity. A priori, this combines into 4 possible cases. The theorem says that one of these 4 cases is impossible. We cannot have a divergent series that becomes convergent with absolute values. I will postpone the proof till the next video. For now, I want to explain how is this theorem useful, how do we use it in practice. Let's say we are studying an arbitrary series. We want to know if it is convergent. In general, the series won't be positive, negative, or alternating, so we do not have many tools that we can use. We can first look at the same series with absolute values and try to find out whether this one is convergent. If the series with absolute values is convergent, then so is the original one. Problem solved. However, if it isn't, then we cannot draw any conclusions about the original series yet. We have to try something else. Let's illustrate this with some examples. As example number 1, let's go back to the motivating question. Is the sum of sine of n over n squared a convergent series? First, I will look at the same series with absolute values. It is a positive series, so I can use comparison test. Absolute value of sine of n over n squared is bounded above by 1 over n squared. And we know that sum of 1 over n squared is convergent. By basic comparison test, so is the sum of absolute value of sine n over n squared. Great! This is the good case. The absolute convergence test tells us that the original series is also convergent. Done. Notice that I could not have been able to use comparison test directly on the original series. The comparison test can only be used on positive series. For a second example, let's look at something a bit more complicated. For each positive integer n, I define the number p sub n as 1 over n, if n is prime, and minus 1 over n, otherwise. I want to know, is the sum of p sub n a convergent series? Think about it for a moment. This is similar to the harmonic series, but I have positive and negative terms. And the pattern of which terms are positive and which terms are negative is a bit chaotic. To attack this problem, I do not have any other idea, so first I can look at the same series with absolute values. In this case, that's easy. It is exactly the sum of 1 over n. I recognize the harmonic series, and I know it is divergent. Unfortunately, this means the absolute convergence test does not apply. I do not know yet whether the original series is convergent or divergent. It is definitely one or the other, but I will have to do more work to figure out which one. As I said earlier, I am postponing the proof till the next video. For the rest of this video, I want to introduce 2 new related concepts. Let's revisit our little table. There are 2 different cells in this table that correspond to convergent series. These 2. Let's give them names. This is just a definition. A convergent series is called absolutely convergent when, in addition, the same series with absolute values is also convergent, and is called conditionally convergent when the same series with absolute values is divergent. These are just names for these two cases. Here are the names back in our table. There is one fourth case, but we do not need a new name for it. We simply call that case divergent. Let's illustrate these two concepts with some quick examples. First, the alternating harmonic series, the sum of -1 to the n+1 over n. This series is conditionally convergent. Why? The series itself is convergent thanks to the alternating series test, but if I remove the signs, if I make all the terms positive, then it becomes the harmonic series, which I know to be divergent. It is a p-series with p equals 1. By contrast, if I look at the same series with denominator n squared instead of n, then this new series is absolutely convergent. Why? The series itself is still convergent thanks to the alternating series test, and the series without the signs is also convergent. In this case, it is a p-series with p equals 2. Okay, all I have done so far is give a name to these two types of convergent series: absolutely convergent and conditionally convergent. That's all. I have not stated any new results. You may wonder, why do we bother distinguishing them? Aren't both types just convergent? Aren't they both equally good? After all, every convergent series represents a number, whether it is absolutely or conditionally convergent. Well, not quite. It turns out that absolutely convergent series are nice. In many ways, they behave just like finite sums. You can do to them all the things you would like to do to series. There are some theorems that only apply to absolutely convergent series. By contrast, conditionally convergent series are a trap. They look nice, but they are nasty. They have some pathological properties. For example, conditionally convergent series are not commutative. This may come as a surprise. It goes against everything we know about finite sums. But that's a topic for another video. I will put a link in the description. For now, simply remember that absolute convergent series are nice, and conditionally convergent series are treacherous.